Okay, so let's talk about the relative basicity of some amines and see if we can find some patterns there that help us understand why the amines have a certain basicity. And to determine basicity, we're going to continue to talk about the pKa of its conjugate acid. Okay, so the acidity of its conjugate acid will tell us a lot about the basicity of an amine. So we have 10.8 for ethylamine, but aniline is 4.6. Okay, so if we look at the pKa's of the conjugate acids here, conjugate acid of ethylamine is the ethylammonium ion versus the aniline ion. So what the pKa's show is that this is a stronger acid than this one is. This one's a weaker acid. Well, if that's a weaker acid, that means that it doesn't give up its proton as readily. That means that this molecule here wants the proton more. And let's look at the other one. If this is a stronger acid, that means that this molecule would give up its proton easily, which means that this one doesn't want it that much. That means that this one wants a proton less. We're so used to talking about acidity, but now let's think about basicity. So if something wants a proton more, that makes this a stronger base. And that makes this a weaker base. If I have a higher pKa for the conjugate acid, that means I have a weaker conjugate acid, which means I have a stronger base. If I have a more acidic conjugate acid, then it's caused from having a weaker base. So now, the question that comes up is why? Why is aniline a much weaker base, 10 to the 6 times weaker base than ethylamine? And of course, I just said why, so you're probably going to say lower energy, which I guess is sort of true, but it's one of our other 5 principles that comes into play. And pause it and think about it for a minute if you can, and then come back. So the main difference between aniline and ethylamine is that this pair of electrons in aniline is in resonance with the ring. So there's a whole series of resonance structures that we can draw. Because amine groups are electron donating, so it's donating that electron pair to the ring. And then I can move that electron pair all the way around the ring to put the negative charge in the ortho position, to put the negative charge in the para position, and to put the negative charge in the opposite ortho position. And if those electrons are in resonance in the ring, in all 3 of these structures, that nitrogen has a positive charge and is not a good base or a good nucleophile because it doesn't have a free pair of electrons ready to react. However, our ethylamine, there are no resonance structures you can draw. That nitrogen has a full lone pair on it all the time. Now let's see if you can use what you know about electron withdrawing and electron donating groups on an aromatic ring to see if you can figure out the difference between nitroaniline, paranitroaniline, and aniline. Which one of these two would you expect to be a better base? So again, it's all about the electron density. And if you think about this electron density is being pushed into the ring, what you need to consider is what does the nitro group do? Nitro is an electron withdrawing group, so that pulls electron density out of the ring. What that will cause is even more electron density to be pushed into the ring than would be normally, to offset the fact that the nitro is pulling electron density out of the ring. So because of that, the electron pair on paranitroaniline is even less available than it is on aniline. So this one is going to be less basic than aniline. This one will be more basic. Now you do the same analysis with aniline and para-aminophenol. Now hydroxide is an electron donating group, so that's pushing electron density into the ring, while the amine is trying to push electron density in the ring also. So now if you think about this, these two are sort of fighting with each other, and the parahydroxy group is making it less possible for the amine to push electron density into the ring than would be in a regular aniline. So that means this one has more electron density and more of that lone pair available on the amine nitrogen than would be an aniline alone. So that one makes this one more basic than aniline, which would then be less basic. So if you want a general rule, you can say that electron withdrawing groups make aniline less basic, while electron donating groups make aniline more basic. Now, I'm not a fan of just memorizing things like that. I think that being able to go through and solve this is a lot better than trying to memorize these facts. Personally, I can't memorize these to say which one is which. If you just ask me off the top of my head, does an electron withdrawing group make aniline less basic or more basic, I wouldn't answer that right away. I would have to go through the analysis of it to say, okay, what happens in that? But that's the valuable skill in this, is to be able to go through and do an analysis of it. Okay, so now let's look at the basicity of pyrrole. So the pKa of the conjugate acid of pyrrole is 0.4. 0.4 is highly acidic. If you think about this now, this is 10,000 times more acidic than a carboxylic acid. So let's try to figure out why. Okay, so that's the conjugate acid of pyrrole. So before I go through and explain it, see if you can pause and figure out why you think that that's so much more acidic. And what that means is that this is a terrible base, right? If that's a very strong acid, this is a really bad base. So see if you can figure out why that is, and then come back and I'll explain it to you. Again, it gets down to one of our 5 basic principles. So I can't overestimate this. The very last thing we're doing in the whole year of organic chemistry, and we're still back to our 5 basic principles of acids and bases, resonance, electronegativity and polarity, aromaticity, and sterics. Remember, those are our 5 areas that we talk about over and over. So the key here is aromaticity. There's a pair of electrons on that nitrogen that are tied up in this ring that make 2, 4, 6 electrons in a ring. With 6 electrons, this ring is aromatic. What happens if we protonate this molecule is now there is no electron at this position. We've lost aromaticity. This nitrogen goes from being sp2 hybridized to being sp3 hybridized. And now with the sp3, this is non-aromatic. So that loss of aromaticity makes this really, really not want to be protonated. So this is really a terrible base. Pyrrole is one of the worst bases of any amine that you can find. It really doesn't want electrons. And pyrrole, if you're going to use it, is not going to be used for a base. Now, look at pyridine and try to figure out what you think is going to be with pyridine, whether it will be a decent base or not. The pKa of the conjugate acid of pyridine is 5.3, which means that it's a bit better base than aniline. Because remember, aniline, those electrons are tied up with resonance in the ring. This pair on pyridine is actually impossible to be in resonance with the ring because there's already a pi bond at that nitrogen. So this pair of electrons is free to react. All right, what about amides versus amines? So looking here, you might think, well, there's a lone pair of electrons on my nitrogen from my amide, so that should be very similar to my lone pair of electrons from my nitrogen on my amine. While the conjugate acid of ethylamine has a pKa of about 10.8, the conjugate acid of acetamide has a pKa of about minus 0.73, which means that it would be a really strong acid as far as organics go, which means this is a really terrible base, even worse than we had before, with lost aromaticity. So why is this such a bad base? And of course, the reason, once again, comes back to one of our 5 areas, and that's resonance. This electron pair is in resonance, and so we have this resonance structure. That's a really important part of the structure of amides. And because that lone pair of electrons is not free either on the nitrogen or on the oxygen, neither one of these is a good place to protonate, and it does not get protonated very easily, which means this is not a very good base. Amides are not basic molecules in general. Now, this has another important factor when you get into biochemistry, and that is the structure of polypeptide chains or proteins has a lot to do with the fact that all of these bonds in the amino acids, all these peptide bonds, all have partial double bond character to them. So there's not free rotation around this bond like there would be around sigma bonds. And because of that, that holds our proteins in the different shapes that we find are standard for each protein.